Okay, so Wordle, or more like using math, statistics, and JavaScript to automate Wordle, so I'll never need to do so again. There'll be a few code examples, and if anyone wants it, you can always go to the Git repo. However, thank you for lasting until the last talk. I know a lot of you are very tired. So to clarify, right, this is not going to be a code walkthrough. You do not need to know JavaScript knowledge, and you're not required to have a statistics degree. I won't be covering complex statistics. It will just be simple counting. So don't worry, it'll be easy. An alternative for my talk would be to call it using math, JavaScript, and aggregation to automate the solving of Wordle. And by aggregation, I really mean aggregation because I'll go through what's the difference between the hard math and the approach that I took later on. So part one, the background context, which the MCs actually have shared in part. How many here have actually played Wordle before? Woo! I see a lot of hands. How many of you are still playing? Wow, good. How many of you do not know what Wordle is? Oh, I saw a hand. Yeah. Yeah, that's very suspicious because that person is probably an imposter, okay? Okay? So yeah, if you've never played Wordle or heard of it, that's hard because it was everywhere. Even the government got involved for some reason. And like every alphabet soup of the agencies created their own Wordle. So, and we had so many variations, be it in Malay, in Chinese, in Hokkien. Shout out to Chian who created the idiom version, Chengu Wordle. Did I pronounce it correctly? Okay, but never mind. And it was the #1 social game until the New York Times acquired it. But however, like once it got acquired, like every other major social game, it started being forgotten to the oblivion. But still, good to see that there were many people who played. But why did I want to automate Wordle? As the MC shared, I sucked at it, and not just my wife, I had friends and relatives who were very competitive with it and like to, hey, what's your score? Hey, what's your score? Shit, I actually failed to solve it. So that kind of sucked, and I was still trying to solve it daily. Most of the time, my score averages 5 to 6 if I'm lucky. So that's how bad I was. Yeah, effectively, this is what I felt like, where everyone was like doing 2s and 3s. Like, how do you get 2s? So I decided to one-up it. I decided to automate it instead. But what is Wordle? So for all the imposters among us, right, I'll summarize the key rules so you can blend in better. You have 6 tries to guess a single 5-letter words. Each try, the characters you use will be highlighted with green, which is an exact match. Yellow means you got the correct letter but it's in the wrong position. And gray character does not exist in the actual word. As a slight footnote, if there are double letters, there are some edge cases regarding yellow, but I'm not going to cover that. If you guess it correctly in less tries than your friends has covered, you get to convert it into bragging rights, quite literally. You get to rub it in the face of other people. And a new word is generated every day for you to compete on. So, how do we solve Wordle? This will be covered in 2 major distinct parts. One is the solver algorithm, which is more towards the math and the computation. And the other part is the UI automation program. For the solver algorithm, there are 3 major categories, and you can probably find articles on each major category on how to solve it. The first one is the AI route. The second one is the hard math, the real correct route, information theory. And the third one is the route that I took, which was a simplified math route. I'll explain why later as well. So for the first route, right, the AI route, right, unfortunately, you need a lot of data, and the only data I have was me, and I sucked at it. So the AI will probably suck as bad as me, so that was a no-go. Then that leaves the 2 remaining route, which required math, so I needed to study up on it. So that led to information theory. This was the hardest part of the whole thing, but yeah, I'm going to simplify it, so don't worry. If anyone wants to read the full math and understand the full thing, this is the simplified version from semi-simplified, which from 3 blue, 1 brown. If you want to hear the full thing, you go do a PhD. Because in essence, what information theory is, right, is branching out all the probabilities and all the possibilities out there and computing it so that we know what's the best option for you. And this actually manifests itself in ways that you may not predict beforehand, and I'll show why more. Because what you can view it is you actually brute force the entire decision tree, every single combination out there. And from brute forcing the entire decision tree, you know that, hey, if you take this path, you are more likely to lead to your success. So this can lead into very weird behaviors, at least from an AI point of view, or not AI, more like the computer point of view from information theory. So take, for example, this case, Saint Moher, I might be butchering the pronunciation, I'm sorry. Somehow, when you are processing it through the large decision tree for the information theory, the computation may decide to give bleep. And I'm like, what the heck? It's like, why did you give it this? Like, for most humans, right, we'll be trying to like figure out words that ends with an R. Maybe we'll try to put an E in the first 3 letters to like try to get a better guess. But no, the machine already knew. It saw all the possible answers, and all it needed to confirm was B, L, Y, or P, whether it was in the letter, whether it was in the word, and once it confirms it through its computation, it already knows its answer. That is how the decision tree and information theory works. And you can think of it like a professional chess player who's multiple turns ahead of you. At every part, right, basically once it gets the result from the input it gives in, part of the tree gets chopped off until all it has left is one answer. Basically, before the last letter was already put in, regardless of what was the result, green, yellow, or gray, it already knows the possible answers already. And like literally, what famously said by Sherlock Holmes is, once you remove everything that was impossible, all you're left, however improbable, is the answer. And that's how it does it. So it will give very weird words for the sake of optimizing the information it gets. So yeah, that's how it does. And so, as you already alluded, this is brute force. And in Wordle, brute force means 2,315 possible answers, assuming standard Wordle. This is before the New York Times changed stuff. There was some stuff that got changed, along with 10,657 additional words. This gives a total possible options, right, of 12,972 words to the power 6. This math formula is not correct. Information theory uses a more complicated formula, but it gives very close numbers. So what that leads into is 4.7 iota, septillion, or quadrillion, or what is probably more comprehensible for most of us is 4.7 million. But it doesn't make sense, for example, if the AI just says this all the time, sane. Or it doesn't make sense to use, like, I can't pronounce this right, Ali, I guess, because it's double A and double I. It's just not useful and to spam this. So in concept, some people have already attempted to optimize this approach on information theory to reduce it down to 2 million, to about 2 million, 2 iota, around there, by getting rid of the really unneeded words. Still, that takes basically forever to compute. And by forever, I mean like a day or two by most modern computers. And basically forever for me. So I wanted it to finish in minutes, not hours. I needed it to compete with my relatives when they say, hey, what's your Wordle score? I needed the answer immediately, not the next day. So that leads me to the simplified math route, what I call the agar-rated information theory. It may not be the very best Wordle solver on earth, but it's better than me, and that's all that matters. So, but then some people will be like, isn't agar-ration cheating on math? And in a way, yes, but in a way, no. It's all about use cases. And I want that to sink into every developer, to you, like remember your use cases. You don't need the perfect O1 or ON answer all the time. Your use cases are important. Because, take this for example, this is from the NASA simulation of landing the Mars rover. They use several supercomputers to compute every single variable and factor just to make sure that even if there's a small pimple on the surface of the vehicle, it doesn't burn up into a ball of flames. And that's important because you're sending a multi-million-dollar craft with millions of man-hours and man-days, all preparation in several years in advance. One mistake that happens, you can't undo it, you can't redo it, at least not easily. On the flip side, there was Kerbal Space Program, which used a simplified math and physics model to bring joy to millions of people as they launch their rocket and as their rockets explode due to the bump on it. Different use cases accordingly. So cheating is fine, as long as you somewhat keep to the spirit of it. And in my case, I will still keep to the spirit of the information theory and the math. So automation ground rules. We are allowed to know the full and answer word list. Because if anything, a computer is good at counting and keeping track. However, we are not allowed to memorize solving sequence lists. This is important because like it gets a little bit too easy if let's say the AI can't remember, oh, on day 100, this is the answer, day 101, this must be the answer, then it's going to get instant solving all the time. Also, I'm not competing on strict mode for now, because the math, or at least me trying to explain it in a talk, gets way too complicated when you do strict mode. TLDR, in strict mode, you do not want to get greens, you want to get yellows. The reason is you can move yellows around to be able to optimize your guess. Greens trap you in too quickly, and you basically lock yourself out. How you decide that is a very complicated topic. So that brings in to the main part, the Wordle solver. How do we apply the math and statistics at it? So, I mean, for a lot of human players, right, you will generally know that your game is split into two phases. One is information gathering, and one is endgame guessing, which is pretty much the last few words. Like, you already know what's the answer, so that's the endgame guessing. When choosing a word, right, the general advice will always, during the information gathering phase, will always be, choose word with as many unique characters as possible. Why have duplicate letters? It's a waste of time. Try to use popular characters. So like alluded, E is a very popular character. Actually, any vowel is popular characters because every word has a vowel. And the faster you can confirm / eliminate these variables, the faster you can remove large chunk of that decision tree. But then the question is, how do we choose what to compute, or what word to choose? So let's quantify this process. So how do we quantify this? So we can quantify this simply by just counting the amount of characters in the answer list. At the very beginning, right, this will be around 2,000 characters. This is not working JavaScript. This is just pseudocode, just to help people convert it into whatever language they need to. So in this case, it'll be column count, unit count, and overall count. These are useful statistics that you can use as you solve it. So column count will refer to, okay, for this column, what's the statistics from the remaining answer that is this character? Unique refers to what's the occurrence of this letter that is unique per word. This is slightly different from overall, which doesn't take into account the uniqueness, as you can see from the code. So if I were to run this, so for example, this is the actual JavaScript. There are some edge cases that I need to take care of, like for example, you can't do an increment on now, so there needs to be stuff that patches over it. It follows the same getting the overall and the positional statistics, counting over all the possible answers and computing it accordingly. So if I were to run this, for example, trying to get the first word character statistics, so that means I'm trying to get the statistics when there's no answers, the very initial blank state. What do I get? I get quite hard to read this JSON, but basically it gives the individual character positions and what's the score. I already pre-clean this up to you into a spreadsheet to make it simpler. So if you're starting a brand new Wordle game, right, this is for each column the statistics of all the possible answers, the characters. And as alluded, E is one of the most common character. So it's AROTL and ISN. So as what you will see later, right, when you're taking this information theory approach, right, one of the most highest probable word that you want to use at the beginning is SAINE, SAINE. Other popular suggestions like crane also has similar statistics. When I wrote an article about it, basically everyone just wanted to know the word was SAINE, and then they stopped reading after that. so that's it. And this is useful because once you get all these numbers, right? What you can do is start scoring words accordingly. So as you score the word, right, you can score it basically by the position index of it plus the unique character score. We use the unique character score as a tiebreaker because actually what we are after, right, is to find the exact green matches in their specific columns as much as possible. But sometimes there's ties, so we added a tiebreaker using the unique score. And And because in general, right, when possible, right, knowing if the most popular character in the list, right, is an exact partial or no match, right, is almost as close to the optimal answer, right, in getting the information that you need. In many cases, right, it reduces your possible word list by more than half. And frankly, that's near the optimal state already. It may not be the true optimal, but it's damn close. I mean, you can get a supercomputer to compute it for you, and you'll find it's not that far off. So, why is sane one of the best starting words? And you'll see it repeatedly used. You can literally see it from the breakdown. Compared to all the answers, right, sane, right, has a 91.06% chance of finding at least one yellow or green. It then has a 55% chance of finding at least two. Compared to other popular words like crane, right, it actually outperforms it in terms of finding at least a single match. From there on, depending on your strategy, it's a little bit subjective depending on what you want to optimize for. So, but yeah, it's almost there. And you can actually get these numbers that I show here in a more easy to read format according to from my script, because I already prepared a starting word match statistic file accordingly. I'm not going to go through the script too much because it's just basically taking the initial word and then checking against all the possible answers quite quickly. And if you can run it against any word, so be it sane, you get the output, or crane, or any other popular words that you may prefer. So if you want to know what's your favorite word's performance, and this could be personal to you, and that's fine, because it's meant to have fun. You don't need to over-optimize the math. You can find out how good that word is. Okay. Why is it repeating? Okay. So once we got all those numbers, right, as what is shown previously, right, we can start to rank words. And the easiest way is to use the positional score and the unique score. This is not the optimal answer, but this is the easiest, and it works fairly well. After you have the ranking function, right, very loosely, right, what you can do, right, with the code, right, is that for each round, right, you get the game state. And from the game state, right, you filter out all the valid words that you can put in. If it's strict mode, this you also apply your strict mode rules. If it's non-strict mode, typically you just want to you want to filter out words that is of low score. Once and it could be actually the full word list. Once you have that word list, you sort it according to your scoring function and the ranking function that was shown previously. After you rank it finish, so if you see down here, the largest score will win the rank. After you score it finish, you can guess using the first word, check whether it's completed. If it's completed, yay. If not, rinse and repeat until you succeed or fail accordingly. Once you have that, you can actually rank your ranking function. So you can have experiments on permutation on how your ranking function works, and then basically test it against the entire Wordle list. So this is all 2,300 days of Wordle computed at one go. And then you get the average score accordingly. So take, for example, this simplified formula. I can run it. And when I say brute force is hard, right, I am not running on this laptop because it takes too long. This is literally 28 cores running on a server somewhere. And just for doing simple positional, this runs takes over 5 minutes. I had to spin up 100 threads, and you can just literally just eat all the CPUs in a few seconds. Yeah. For the convenience of time, because I'm not going to wait that 5 minutes, I'm just going to show the answer. If you see here 21 minutes, yeah, that's because this is single thread mode. So if any of you want to play around the code, there's the single thread mode, one score ranking function single thread mode, and there's the multi-threaded mode. Oh, it's already throwing failed answers here. If you see accordingly, it will actually throw out what it failed to match, and it will dump the game state accordingly. So you can see the game state like bad character set. There's a lot of debugging stuff. What's the good character set? What it actually found so far, and what is the words that it tried. So and of course you actually know the actual letter. So you can actually figure out most of the things from there. Yeah. So, like I said, even in its simplest state, right, even in its simplest form, right, this this would have been passing 2,289 times, failing 26 times. So it was around 98% there, 98% of the time. And the average score, oh wait, I think there's a bug in the average score here. The average score was around 4 point something. Once again, better than me. In fact, that version 1 was enough to beat most of my relatives. But at this point, it's no longer about relatives anymore already. It's about how do I get this to 100%. So the next step was improving the ranking function. So same thing, we apply information theory accordingly. Like, we want to use words that will give us information. We want to penalize words that do not give us information. So what does not give us information? Duplicate characters. What also does not give us information? Penalty for known or useless characters. So what I mean by known or useless character means we already know that it's failed, gray. Or we already know it exists in the word, yellow. We can penalize those accordingly so that we can prioritize getting as much information as possible at each stage. So this can be shown accordingly. So all the ranking functions are here. So for example, the implementation was simple. This is the documentation for all the information provided to you. So for each position, this is the simplified version, version 1. In version 2, actually subsequently, I started letting it bias into unique words. Subsequently, for version 3, I implemented the logic for it being aware of, let's say it's in stage 1. So that means it's just trying to get information, and subsequently the last 2 rounds, it'll just prefer to, you know what, I'm just going to guess it. Finally, in version 4, 3 has a lot of experimental code, so you can see all the random trial and errors I went through there if you want. In version 4, basically it ran through what was the refined version that I went through. When it detects a duplicate character, I don't score that letter. So that already automatically bias any other character that is not duplicate. Likewise, if it's already in a known bad character, I don't score it. It's important to still allow these characters to be allowed to be inputted. The reason is because there are cases where the Wordle of the day has duplicate letters. So if I were to outright say no and negative, I will never solve those situations. Likewise, if I already know the position, I skip accordingly. However, what actually made it break into getting it 100%, right, was this. Whenever I enter a situation, right, where let's say a specific column I already know the answer, what I do instead, right, is that in that column, I try as much as possible to match against other positions what is the most probable letters and use that accordingly. Basically, I'm trying to get yellows here, and I ignore any other letters that I already know are yellow. I'm trying to get new yellow blocks in this tile, and I optimize that accordingly. So to run this respectively, I can run it again. Has this finished? Yes, it has finished. So I can run this at v4. Where's my v4 version? Oh, I think it gone to the wow. Let me copy this. Rename, copy. Yeah. For the convenience time, once again, I'm just going to skip to the actual answer. And in this case, for the v4 version, it finally hit the 100%. And that was to me like, yes, success. But like, what was more amazing for me, like actually digging in the code and seeing it run continuously, right, was actually trying to understand how it works. So I'm just going to go further into like explaining it in details. How the solver approximately works step by step, because like prelude, the blight thingy, it's confusing. But once you have the code, you can start computing all those scenarios. As short, I can dump the game state at any point in time, and I can dump the statistics at any time. And that's what I did. So this again, how did it get ulcer? So at the start of the game, as I already ran through, sane makes sense. It was the only word that covered as much of the top letters as possible. So you see, 5 out of, it covered most of the top few unique letters, and it covers all the top letters, almost all of it at the top here. except for the duplicates. And he only found a partial match E, but he found that there was no match with SAIN. Using that alone, right, from the total possible of 2,315 words, right, it got sliced down to 187 possible words using that information alone. And from here onwards, right, because I know that E existed somewhere, but not in the last column, right, basically it was just trying to find any words with it knows that if the E has to exist somewhere in the first four. That's why you see a very strong bias there. However, but if you remember back in the code that I ran through, I avoided rerunning letters that I already knew. So what I tried to do is pick M-O-U-R. In fact, at this point, it doesn't even care what's in the middle column anymore, apparently. So M-O-H-U-R. And the chosen word is that because, but if let's say I score anything here, it will score very highly between the remaining words. And when that happened, when M-O-H-U-R ran through, from the remaining score, right, from the known new information, it reduced the amount of words known left to 12. At this point, you can already see the answer here. This is the remaining word sample. So this is a sample of the 12 words, the list of the 12 words. And you can see why it tried to use blight. Because in one shot, right, if any of these letters match, right, it knows very clearly. Like even if let's say P matches here, you can see there's only one word here with P. So it already knew the answer approximately at this point already. It just needed to know which version of it. And likewise, as L was matched, there's only, as you can see, there was only two possibility. But if you were to look through all the other ones, so where was the other one with L? Also other bluer. Bluer. If you realize it couldn't be bluer, and from then on it just guess its also respectively. So this is what I mean by reducing the information space based on the guesses. You can see a much faster example. For example, when it uses the same approach to literally guess from sane, once again, straight away with the information it has at hand, from the greens and the yellow, it reduced the information down to 12 possible words. And from there on, P ranked very highly, and U and T. Once it ran that through, the information gets basically reduced down to Pluto. So yeah, that's how it works. The solver works at a high level. But at this point, it was not enough, because you see, not all my relatives are tech, you see. And I can say, yes, I got the best solver, but then if I show them command line output, it's no fun. So I needed to show them screenshot. And I needed to automate this part. So that's the next part, integration with the UI. It's actually just taking the same approach, using a ranking function to solve the Wordle, but on the actual website. And how do we do that? So, live debugging with the Wordle code. Where was it? Okay. I'm using the mirror because this code is actually not updated for the New York Times version. So you can actually get all the information you need in the HTML. You don't even need to extract it from the JavaScript. There has been some approach to getting the information out of JavaScript, but that's not really important. So let's say I just do sane here, for example. As I type it out, you can actually extract the information here accordingly. So you can see for the row and the column, I can get whether it's correct, absent, present accordingly. And I can even double check that I input the characters accordingly. This is all the information that I needed to check, and it's all about literally doing the respective XPath, CSS selector, jQuery selector, whichever preference of choice to extract the information out. And that's basically what I did. So for the selector, you can see it here. So you can literally see from the query selector from the game app, take from the shadow root because it's a shadow DOM, game team manager, board, game row, extract the absent, present, correct information. Using this information, likewise, in the very same loop that's shown previously, get game state, feed it into the solver, rank it, run it, rinse and repeat. And And once you have that, all I need to do was just piece everything together in an easy way for me to just share with my relative. And that's the last start, where, wrong, where I can just run it as a snippet. So if any of you would like to play around with this, right, you can write your own solver function. You can write your own ranking formula, choose accordingly, modify accordingly, and then once you generate it, you can generate a snippet where it's running live. So in this case, as you can see, it's running. This is today's Wordle. It's still running, but once it gets the solution, I can just take the screenshot and send it to my relative. And please don't fail me today. Yes, it's solved. Okay, yeah. Woo! I did not check whether it will work, so I didn't expect it to reach 6. Okay, so yep, that's about it. My name is Eugene. You can ask me anything from this point onwards. I go by the handler Pico Creator. You can find me on Twitter, GitHub or Stack Overflow, mostly on Twitter. I've been working in various companies and startups for the past 12 plus years. My open source projects, my most popular one is GPU.js. Another one that's fairly popular is Inbox Kitten. I'm currently the CTO at uilicious.com, so forgive me for shamelessly plugging it in. It's an online platform that does web test automation, and I believe that internet testing should be a piece of cake. I talk too much about internet infrastructure and software architecture, so feel free to reach out to me.
Yeah.
Okay.
If Cypress was a company, but it is.
Okay. Any questions?
Any questions? I'm gonna look through like the online Slido. There's nothing on Slido. Hi guys, anyone? Any question want to shout out? This is someone who is very like. I'll pass you the mic. Give me a while. Let me slowly walk over. No more energy. Sorry. Yeah, here you go.
Going all the way back to the 3 blue, 1 brown video. I watched a similar video and actually made a similar project after watching it.
Flex.
No, not Flex. It was probably worse. A lot less complicated than this one. What do you think of... I used something called entropy in the information theory. Did you experiment with that at any time?
Actually, yes. So basically, like, right now what you saw was the a lot more simplified version. I actually did try to do the approach more similar to what 3 blue and 1 brown did. I actually started this project before this video came out, but when I launched the article and then his video came out, so basically everyone just kept diverting me to here. So I decided to reference it because he covered it way better than I understood it. In fact, my understanding of information theory was, I would say, garbage until I watched this video. But I did try to do the similar approach on it, and I just started realizing it was just taking too much compute. And yeah, you can take that into account, but if you realize like what I showed in the numbers, right, I'm just basically abstracting it away by just using the highest scoring number. According to information theory, what is probably the best option, right, is not the highest scoring. Because the highest scoring is information that you already know is probably, because if let's say I'm oversimplifying the math here, so if let's say you already know 80% chance that it's going to be the letter E in the 4th column, why even bother trying to guess that? Maybe it will be better, right, to find something that's at a 70% chance and you input it in there. But that became a snowball effect until like it became more complicated, and I did experiment with it, and I keep finding my algorithm keep performing worse and worse. It may do a better score, like it may even make guesses in like 3.1 or 3.2 on average, but it can never get the 100% solving rate. There was always that, and it could be my math error. So even for 3 blue 1 brown, for example, right? There's actually a follow-up video where he found his math error, and it's very hard to get the math correct. And literally, there are PhD students writing papers on it till today on how to get the math right. So I'm not going to claim to have succeeded in any stretch. But yeah, they try to go through that path, find it that it was less efficient than this, and somehow scored less. So I was like, you know what? I got this working. Go for it.
Yeah.
Yeah. That's why back to approximation.
Awesome. Thank you so much.
Cool. So, fun fact: you can actually solve like Wordle in 1. They used to be like the answer sheet in the JavaScript if you know where to find.
That's where I extracted the word list
Yeah,
from.
just use the answer key. Is there any more questions? Can be about the person itself. It's running a UI-licious, right?
Sure.
Actually, very curious about like how. Oh, crap. Go. Wait. You wait.
This is
You wait.
online. People online needs to hear.
Yeah.
Okay, so you said you're like the CTO of UILicious, right? So what made you like join UILicious, or what's the purpose?
Oh,
behind
so
it?
I've been working in like I shared, I've been working in the industry for like over 12 years, and I guess there were too many late night deployments. Or for me, the worst case was there was one time where I was working on a project as a vendor, and the CEO of that company of that bank, right, decided to announce, hey, we're going to launch said mobile app 1 month ahead of schedule, and they basically told us to just speed up everything. Testing and testing will be just an afterthought. That was a complete nightmare. There were so many late nights just running tests, getting things to work and all that. And I'm like, we are doing this manually. We should automate it. And that's why I wanted to build a test automation tool. And that's like another topic on its own. We try to make it easy. I didn't want a test automation tool for engineers because in that scenario, the PM was like, engineers are too busy launching features. We cannot use them for testing. So we decided to make a tool that manual testers can write test automation for.
Oh, so this is actually a tool for like test engineers, not for.
Both test engineers can use it and manual testers can use it.
Right. Cool.
But in this case, I'm writing off that tool. So if you can see the command, the commands are actually very simple. At least until I throw in all the math solver, it's literally I go to, I see, and then it goes starts, I click. Yeah.
Right, like that's cool.
Yeah, that's until you throw in the giant JavaScript on how to solve Wordle and on the Wordle dictionary list. Yeah, and yes, the answer
Fancy.
list is in here.
This is the answer list, by the way.
Yeah, correct. But I set the ground rule. I'm not going to cheat. I'm just going to reference this as the dictionary.
Why not cheat? It's so easy. Always solve in one. Okay.